Alright, in this video we're going to do a lot of practice questions. There's going to be 7, it's going to be a little bit long. I recommend you pause the video after I write down each question, since I'm not going to take the time to say, okay, pause the video, try it out. So you can follow along, or you can pause the video after each question, try it, and see if you can get it. So we'll start out right away with our first question. It's probably going to be one of the harder ones. I'm going to throw it to you right off the bat just to throw you guys off a little bit and step your game up. We're going to take the limit as theta goes to 0 of 1 plus theta squared minus cosine squared all over theta squared. And first of all, don't be afraid by me changing variables. It's all the same. It's just a different letter. Instead of x, we use theta, a Greek letter. And there's a couple tricks we're going to do here. So first, we're going to rearrange this top equation to be the limit as theta goes to 0 of 1 minus cosine squared theta plus theta squared all over theta squared. Now, what do we know? Let's use a trig identity here. 1 minus cos squared is going to be equal to sine squared. Why is this? In fact, I'll write this down right here. We know that sine squared theta plus cosine squared theta is equal to 1. If you do not remember this, please try to review your trig functions. These are very important for these equations, especially if you want to make this work. So 1 minus cosine squared is going to be sine squared theta plus theta squared all over theta squared. So it's still difficult, and what we can do is we can break this up. So we can say the limit as theta goes to 0 of sine squared theta over theta squared plus theta squared over theta squared. Okay, now what we can do here is we can recognize that theta squared over theta squared is equal to 1, and sine squared theta over theta squared, this is a little bit trickier to comprehend, but remember that sine squared theta is the same as sine of theta all squared. So we can factor out the square, so it's sine theta over theta squared. Now what's interesting here, I'm not 100% sure if I mentioned this, but the limit as theta goes to 0 of sine theta over theta is equal to 1. This is a very important formula. In fact, to make it more general, the limit as theta goes to 0 of sine of k theta over k theta is equal to 1. So if there's a constant out front, k, then as long as it's on the bottom, it's also equal to 1. So these are two very important formulas. If you didn't know them already, I'm terribly sorry. You're learning them right now. These are very important for calculus limits. You're going to find some very, very tricky functions. So this is the same thing as saying that the limit as theta goes to 0. Actually, we're done with limits. We can just plug it right in. This is equal to 1 squared plus 1, which is equal to 2. That was the first limit. Couple tricky trig functions that I might have not mentioned, but you probably should know, so remember them here if you're going to remember them anywhere. These are very important. Okay, question number 2. A little bit easier. In fact, this comes from one of the very first lessons. We're going to find the limit as x goes to 0. Notice how we like going to 0 of x divided by the square root of 2 plus 3x minus the square root of 2. Straight away, multiply by the conjugate. So that's 2 plus 3x plus root 2 over the root of 2 plus 3x plus root 2. Okay, so what did I say about multiplying things out? Generally, we leave one of the sides just not multiplied out at all because we hopefully want to cancel things. So we're going to try to do that over, well, this is the same thing as 2 plus 3x minus 2. So these 2's will cancel. The x divided by 3x will cancel. So we're going to get the limit as x goes to 0 of 1/3 times the root of 2 plus 3x plus root 2. And when we plug x equals 0, we'll get 1/3 times root 2 plus root 2, which if we do the math very quickly on this, This is the same thing as 2 times root 2 over 3. We could do some weird things with it, not gonna because it's totally not necessary, but here's your answer of 2 root 2 over 3. Again, the trick here is multiplying by a conjugate. I'm trying to show you a different trick in every single limit because these tricks are not even really tricks. We call them tricks, but they're actually strategies. We're just trying to make people feel not bad for not knowing them right off the bat. They're not tricks, they're strategies and techniques, so please, please practice these techniques. They will save your butt in calculus all the time. Alright, question number 3. Here is a nice limit at infinity question. We're going to take the limit as x goes to infinity of 5x squared plus 26 minus 3x over 42 plus 10x squared. Now, don't let this trick you. We have some nice leading terms here, x squared over x squared. These are the highest terms, they're equal. So if we do a quick trick, this is the same thing as saying 5 over 10, which is 1/2. And this is the limit. Now I will write this out the full way, so we're going to divide the top by x squared. So we're going to get 5 plus 26 over x squared minus 3 over x divided by, well, this is going to be 42 over x plus 10. And as x goes to infinity, all these terms will go to 0, so we get 5 over 10. This is the long way. Again, both ways are fine. You should probably write on an exam either the full way or mention a theorem of some sort that if you have, like, say, 5x to the p over 6x to the p, it equals 5/6 or something. Something along those lines, just as a general indication that you know what you're doing. So that way your prof can see, oh, hey, look, he knows the material really well. He's done enough practice problems that he knows exactly what's going on, and that should be hopefully sufficient. Okay, question number 4. We're going to do a continuity question. We want to know if g is continuous at x equals 1. I haven't given you the function yet, so don't panic. Okay, g of x. This is a piecewise function in 3 parts. It is going to be x minus 2 when x is less than 1. It's going to be x squared plus 1 when x is equal to 1 or less than 3. And it's going to be k divided by x, where k is some constant, when x is greater than 3. Okay, the first thing we want to realize is that we're looking at x equals 1 and we're looking at continuity. So what is the definition of continuity? A function is continuous if the limit as x approaches a of a function f of x is equal to f of a. Okay, so let's figure things out here. What is f of a? Well, our a is 1. We're finding x equals 1. So in our database over here, let's go, well, f of 1 is equal to, well, it's equal to this thing right here, so we plug 1 into x squared plus 1, which is equal to 2. Okay, so our limit has to equal 2. Now let's take the limit as x approaches 1 from the right. Well, when 1 is from the right, we use this function x squared plus 1. Okay, so this is going to equal to 2, because we plug 1 into x squared plus 1 and we get 2. That's good. Our right limit is good so far. Now let's take the limit as x approaches 1 from the left, and because 1 is going, or x is going to be less than 1, we're going to use x minus 2. So x minus 2, we plug 1 into x minus 2 and we get negative 1. So this is a problem because, well, this means that the limit does not exist. Because the left does not equal the right, therefore the limit does not exist. Therefore, this is not continuous at x equals 1. You must remember the definition. This definition is continuity, which means that it has to be broken into 2 parts. 1, this has to exist, f of a, and the limit as x approaches a of f of x has to exist. Now, what does this limit mean? Well, we break apart the definition, which means that the limit as x approaches a from the right of f of x is equal to the limit as x approaches a from the left of f of x. So there's a bunch of things going on in these definitions that all build up from each other. So you need to know your foundations to get further along. So this is a full breakdown of this problem, and hopefully you understand why this is not continuous. If not, please review that section. It is very important to know what continuity is, and why things are continuous and why some things are not continuous. Okay, number 5. We want to show that our function f of x equal to x cubed minus 4x plus 1 has 2 roots, at least 2 roots, on -3 to 2. Okay, so you might remember this is an intermediate value problem. And what I said before with intermediate value problem is that you check the first value and you check the last value and you see if it crosses 0 at some point. But we're looking for at least 2 roots. In fact, there might be more. There might be 3 roots on that interval. I'm not 100% sure. So we're going to check out every single point. -3, -2, 1, 0, 1, and 2. Okay, so I'm going to make a little graph here. -3. When we have f of -3, then we have... Actually, let's not do this. When f is -3, our value is going to be, well, we're going to have -3 squared, which is -27. -4 times -3 is plus 12 plus 1. So this is -15, so this is -14. Okay, that's a really big number. Let's check out f of -2. Well, this will be -2 cubed, which is -8, minus 4 minus 2, which is plus 8 plus 1. Okay, so that's 1. So we know there's a root between -3 and -2. So this is our first root. This is root number 1. Okay, so let's check to see where it crosses again. Let's check f of -1. Well, that's -1 plus 4 plus 1, which will be 4. So it still hasn't crossed the x-axis again, as far as we know. 1 to 4, 4 is greater than 1, it doesn't go to 0. So there's no root there. F of 0, this will be 0 minus 0 plus 1, which is 1. Again, it hasn't crossed that axis. F of 1, let's try this one out. Well, that's 1 minus 4 plus 1. So this is -2. So we know there's another root on -0, or -0, positive 0, and 1. 0 isn't negative or positive. So there's some root between these two numbers and between these two numbers. And let's check to see if there's another one, because I said at least 2 roots. So we found at least 2 roots, but let's check the last one for fun. Okay, 2 cubed is 8, minus 4 times 2 is 0, plus 1 is 1. So actually, there's another root there, on -2 and 1. So we found another root that we didn't need to find, but we have proven that there is at least 2 roots on that interval. So if you found any 2 of these 3 roots, you have successfully answered the question. Congratulations, these problems are not always the easiest, the intermediate value theorem questions, but I chose this very long example just to show that you sometimes have to do more than one point, because in my examples in the previous video, we didn't get something as detailed as this. It was just show one root. Okay. Now we're going to go to another question, number 6. There are 2 more questions. So we want to evaluate the limit as x goes to positive infinity of sine of 1 over x squared. And I'm going to let you guys know something here. If you can do this right now, you have done something that I have not taught you in a video yet. What we're going to do is we're going to do a substitution. And this might seem scary to some people. That's okay. We're going to say let z be equal to 1 over x. And we're going to say, well, what does z do as x goes to infinity? Okay, well, as x goes to infinity, in fact, we're going to take the limit as x goes to infinity of 1 over x. And what do we know? Well, as x goes to infinity, then we get 1 over an incredibly large number, which is equal to 0. So we can say that z tends to 0 as x goes to infinity. So what can we do now? Well, we know our substitution of 1 over x, so we can rewrite this as the limit as z goes to 0 of sine of z squared, since 1 over x squared is equal to 1 over x squared. Like, these two are equivalent, so we know that this is also z squared, so we can plug our z into this position right here. This is the most complicated question you're going to get in limits. It's substitution, so you might have to do this example a couple times to understand why I'm doing these things, where I'm going. I'm doing it because, well, to be honest, if we go x equals positive infinity into x squared, then we just get sine of 0, which, I mean, in my opinion, it's totally okay just to plug it in right away. Honestly, I would do it. Don't judge me. I would do it. My profs would be probably okay with it. It's a very advanced technique, at least compared to what you're doing right now. So let's just finish the evaluation of this. So limit as z goes to 0 is the same thing as sine of 0, which is equal to 0. So personally, I would just say, well, what is sine of 1 over infinity? Well, that just tends to sine of 0, and that equals 0. And that would be sufficient enough for me. So there's an alternate way to do it. I showed you the tricky way because substitution is something you'll be doing a lot in Calculus 2, and it's good just to get exposed to it. You don't have to do it, just get exposed to it so you understand it, and you can get some practice familiarity with it, because when you do have to do it, it's better to go into it knowing what it is than just going into it blind and saying, what the heck is going on here? I have no idea what's going on. Alright, we have one last question for you, which I did promise that there would be a squeeze theorem question on here that would be very difficult. So, we want to find the limit as x goes to 0 from the right of square root of x times e to the sine of pi over x. And you're saying, Trev, you told me last video that all of these trig follow the same pattern, but we have an exponent in here, and I have no idea what the hell to do with that. That looks scary, and we're going to 0 from the right, so what's with the conditions here? I'm going to say, don't panic. Don't panic. Let's do the same thing we started out with. Took sine of pi over x. What are the minimum and maximum values sine can be? Remember, this is the period. It does not change the maximum or minimum values of a function. So we know that the minimum is -1 and the maximum is 1. Okay. Now we're going to raise each side by the power of e. So we're going to raise each side by e, I should say. So here we are. E to the -1 is going to be less than e to the sine of pi over x, which is less than or equal e to the 1. So we've raised all these to be powers of e. The direction is still going the same way because e is an increasing function. I'm going to repeat that. These directional signs stay the same because e is increasing. If it was a decreasing function, there might be the chance that e to the -1 is bigger than e over 1. If that was the case, the signs would have to change. Make sure this is in order from smallest to largest. If not, you have to change the signs around. In this case, it's totally okay. Alright. Now, we'll just multiply each side by the square root of x. So we have x times e to the -1, which is less than the root of x, times e to the sine of pi over x, which of course is less than the square root of x times e. I'm going to leave out the 1, it's not necessary. Alright, so now let's take limits. Okay, so I will do this separately, just so I don't confuse anyone what's going on. The limit as x goes to 0 from the right of the square root of x times e to the -1, well, that's just the square root of 0 is 0, so that's 0. Okay, cool. And we'll take the limit as x goes to 0 from the right of the square root of x times e, which again is equal to 0. Therefore, the limit as x goes to 0 of the square root of x times e to the sine of pi over x is also going to be equal to 0. Awesome, that's Squeeze Theorem. This is the amazing power of Squeeze Theorem. Find minimums and maximums, raise them so you get these smaller and bigger functions, and suddenly you found a very difficult limit without any problems whatsoever. So this was the limit practice video. I hope you found this very helpful. I'm going to cover a couple more sections about limit functions at points, and then we're going to do another practice video, so I'll bring back a couple harder problems with some new material, and that'll be the end of our limit section before we head into derivatives.